students, I would just like us to look at some exact problems where we are applying these equations, these specific equations. So if you're asked for delta G, meaning not at standard condition, being given pressures or even concentrations. If you're at equilibrium, then delta G is 0. And so therefore, we could then use this equation to solve for delta G naught, if you're asked for that. Okay, this first equation here, you are given your reaction, you're given the delta G naught, and it's asking for the value of K sub P. So what we would want to do, at equilibrium, the delta G would be 0. The delta G is 0. So we would apply this equation. I'm plugging in my delta G naught. I've chosen to change my delta G naught to joules per mole, so I can just use the 8.314 joule per Kelvin mole. Then your temperature, that equals your natural log of K, taking, of course, inverse log of that. Then I end up with that value for K. So you can see we're largely favoring right. We're largely favoring right for that situation. Okay, for this next one, I needed to add that it was happening at 25 degrees Celsius. We're given this reaction, we're given delta G naught, and we're given the pressures of our reactant and product, and asked in which direction will the reaction proceed? In which direction? Now, I think that Zumdahl is very confusing with his presentation of this information. And so in your note packet for the relationship of pressure and Gibbs free energy, I have communicated what he is saying. So whenever he's solving for delta G, when delta G equals 0, then K will equal 1. In other words, that we're at equilibrium. When delta G is less than 0, so this is kind of like how we interpreted Q in comparison to K. Okay, if delta G is less than 0, then that means we need to shift right. We need more product to reach equilibrium. When delta G is greater than 0, we have too much product. We have too much product, so we're going to have to shift left to reach equilibrium. All right, so if we go back to this problem, whenever you solve this, now our delta G is negative 5.40 kilojoules per mole. When you solve, and I have the work here, all right, you get 2.05, or 205 rather, joule per mole, I'm sorry. And in comparison, this is much larger than this negative value. So we're larger, that means we are going to shift left. The reverse reaction is favored. But then it says, in which direction would the reaction proceed to reach equilibrium? If these were the partial pressures, well then if you solve that, we get negative 6,319. Comparing that, this is lesser, so thereby we will shift right to get to equilibrium, or we will be favoring right. Then, in this equation, using this information, we're given partial pressures, we're given our temperature, it's asking us to calculate delta G. Well, we know, per our equation, if we're asked for delta G, it's delta G naught plus RT ln of Q. We need delta G. And to find delta G, we know it'll be the summation of the delta G of product minus summation of reactant. And so that's what I found here. So my delta G naught for this reaction is here. And then we would just apply the pressures as I have them. Now you just have to be careful that you are placing everything where you need it to be. So our pressure of our products, take into account the law of mass action, which lovely here, it's only to the first power, divided by the pressure of these guys, first power. So it's just being careful of your math. This ends up being natural log of 50, doing all the interpretation. This is the delta G that I get. And we're not asked to do any kind of interpretation from there, just to get the value of delta G.